Thanks everybody for coming to the second weeks of Atom. This week we're going to talk about Introduction to Tropical Curve Counting. If you attended Diana's lecture last week, you learned about tropicalization, and what she started the lecture with is the slogan, right? That tropical geometry is a combinatorialization of classical algebraic geometry. And the standard strategy that one, hopes to employ tropical geometry for is to simplify some classical algebra geometric problem by turning it into a combinatorial problem that then can be solved, right? And numerative geometric problems are kind of a prototypical example of, when this process can work. So I would like to start real quick just by and not assume that everybody's familiar with the numeric geometry. So just use a couple slides to talk about it. So a prototypical question in a numeric geometry that we've all heard about and dealt with and answered at some point in our lives is what we're going to call N1. It's how many lines pass through two general points in the plane, right? So this is a silly question, of course, but let's observe what ingredients are here, right? So one ingredient is there's geometric objects that we care about. In this case, they're lines. There is a set of constraints that the geometric objects have to satisfy. In this case, constraints consist in incidence to points. You want your line to have to pass through points. And then there's baked in a notion of genericity. In this case, the genericity that we require is that the points have to be distinct, right? And if we look at the picture, we see that if we were so unlucky or unwise as to pick the points to be coincident, then instead of having the solution that we'll expect, that there is a unique line between 2 points in the plane, we actually have infinitely many such lines going on. All right, so we all know the answer to this problem, and we've all probably answered this problem in high school, and we've done it like this, right? We said, okay, the equation for the general line in the plane is y equals mx, right? And then if I have a point P1 with coordinate x bar 1, y bar 1, you can plug in, right? You have y bar 1 equal, mx plus b. I'm not assuming the line is going through the origin. Y bar is equal to m x1 bar plus b. And now you do the same, y2 bar equals m x2 bar plus b. And now x1 bar, x2 bar, y bar, y2 bar in numbers. So what you see here is a linear system, knows m and b. You can solve it and you find the slope and the y-intercept for that unique line that satisfy this condition, okay? So now I want to reinterpret what we did in high school in a slightly higher tech fashion, right? Which is as follows, right? So M and B, right? I can think of them as actually being coordinates on another plane, where each point on this plane gives me a slope and a y-intercept for a line. So this plane is what's called a moduli space for the geometric objects that we're interested in, right? And so every point in this plane is a line, right? And when we when we plugged in the coordinates of a point and we found a linear equation, right? We found that there is a line worth of lines that pass through the given points in the original plane, right? So the set of all lines that satisfy the constraint of being incident to a point is a line in this moduli space. So it's a subvariety of this moduli space. At this point, if you want multiple constraints to be satisfied simultaneously, you're just going to intersect the corresponding subvarieties. And so our question of finding the number of lines to 2 points has been transformed into a question of intersection theory of moduli spaces, right? And so this is kind of both the slogan and the modern technique that we've been used to solve a numeric geometric question. Okay, so that said as an introduction to numeric geometry, let's move on to tropical geometry and tropical curves, right? So last week, Diane introduced every one of us to tropical curves in a few different ways. But for the purposes of this talk, I want to just think of a tropical curve, a plane tropical curve of degree D, as a graph which is dual to a subdivision of the scaled simplex delta D. Here's 3 examples, and I should mention that I have been highly trained by my co-author Hannah Markvik to use the max convention instead of mean convention. All of my pictures will look sort of upside, kind of flipped with respect to the origin, with respect to the Diane's. Hope that doesn't disturb anybody too much. But in red, we have the examples of 3 tropical conics. And let me remind you that edges sometimes have weights, and these weights are equal to the lattice length of their dual segments. So in particular, in this middle picture, the vertical edge that goes down has weight 2 because the lattice length of the horizontal segment to which it's dual is 2, right? And then at every vertex of a tropical curve, the balancing condition is satisfied, which means let's look at the primitive vectors in the directions of the edges. Let's call them P sub EI, and let's compute the weighted sum, the summation of the weight of the edge EI times the primitive vector of EI, and this is equal to 0. Okay. And even if you skipped last week's classes and this is all you know about tropical curves, you'll be good to go this week.
So there's a question about what is the lattice length for the interior curves?
Yeah, so what is the lattice length? So let me draw a little picture just to illustrate this. So all these pictures are happening in a plane that has an integral lattice in here, right? And so in particular, all these segments right here have endpoints on the lattice. So for example, this segment will look something like this. And the lattice length is just counting the intervals between points of the lattice that constitute the segment. So for example, this segment has like lattice length 2, but for example, if I take a segment of slope 2, this only has lattice length 1. Okay, great. Thanks for the question. Enough. This, come back. All right, so now, our first example of tropical enumerative geometric problem concerns just intersection of plane curves, right? And the first thing we're going to talk about is what it means for intersections to be transverse, right? So transversality is a property that we expect to hold generically. So if you were to throw 2 tropical curves on the plane while blindfolded and having been spun a few times, then you would expect to fold them on the plane and intersect transversely, right? So what this means in particular is that they should intersect in a finite number of points. And these points of intersection should not be vertices for either of the curves.
So there was another question of what is delta D, the dilator of the standard simplex.
Yeah. So let me again draw a picture to illustrate this. Get my thing here going. So delta 1 is sort of the standard simplex that has endpoints 0, 0, 1, 0, and 0, 1. And delta, this is equal to delta 1. And delta D is simply when I replace these 1s by these, right? So I'm actually blowing up this simplex by. All right. So going back to transverse intersection of curves, right? We have 3 examples here of tropical lines in the plane, right? And this first example is non-transverse because the two curves intersect in infinitely many points. You don't expect this to happen generically. The second example is non-transverse because this point of intersection is a vertex of gamma 1. Whereas this third example is an example of transverse intersection because we only have one point of intersection, and this point of intersection is in the interior of an edge of gamma 1 and in the interior of an edge of gamma 2. Great. So when two tropical curves intersect transversely, what we're going to do is we're going to attach to each point of intersection the notion of an intersection multiplicity, or a multiplicity of intersection. And we're going to obtain it as, well, if edges have weights W1, W2, and have direction vectors whose primitive vector is denoted P1, are denoted P1 and P2, right? Then we're going to define the multiplicity of intersection of these two tropical curves as W1 times W2 times the absolute value of the determinant of the matrix of the coordinates of the primitive vectors in the directions of gamma 1 and gamma 2. Now, this is a mouthful, but let's just look at what this means in this example. Right? In this example, we have one point of intersection P. The edge of gamma 1 has weight 5, the edge of gamma 2 has weight 2, and the primitive direction in the direction of gamma 1 is 3, 1, and the P2 is 1 minus 1, right? And the multiplicity of intersection is the product of the weights, so 5 times 2 right here. And then all I do is I create a matrix by, putting the primitive vectors as columns of this matrix, right? So I have the vector 3, 3, 1, which is the vector P1, and the vector 1, vector P2. And then I can compute the determinant of this matrix. In this case, minus 4, but I only care about its absolute value. So it's 4 times 5 times 2, and this intersection multiplicity is 40. Okay? So, and there's good reasons to have a definition of intersection multiplicity like this, especially if you're familiar with toric geometry and with the fact that tropicalization is closely related to having a subvariety that lives inside a torus. But I want to take a more naive approach and I say, well, why could this be a good node of intersection multiplicity? Well, for one thing,
Renzo, question from the chat.
Yeah.
Do we always assume that the tropical curves are embedded into some Euclidean space?
Yeah, so for this particular lecture, we're going to assume that these are tropical plane curves. Right? They're going to be embedded in the plane, right? There are several other applications that I'll mention later at the end of this hour and then next hour when that will no longer be the case. But I will make sure to point out that we're leaving the plane world. At this point, everything that I'm saying only holds for tropical curves in the plane. Great. But again, going back to our question of when is a definition good in mathematics, one perspective that one can take is very utilitarian of saying a definition is good if it works. And what does it mean it works? It allows us to prove theorems that are reasonable and good and kind of expected, right? So in this case, there is a classical theorem called the theorem of Bézout, right? And in classical algebraic geometry, the theorem of Bézout says that two plane algebraic curves over the complex numbers of degree d1 and d2 always intersect in d1 times d2 points if you count their intersection with appropriate multiplicities, that in this case are algebraic multiplicities. And we now have a tropical Bézout theorem right, that says exactly the same result holds, right? So if we have two tropical curves, plane tropical curve, degree D1 and D2, and you assume that they intersect inversely, then their total intersection, which is the sum over all points of intersections of the multiplicity of intersection P, is precisely the product of the degrees, right? And the fact that Bézout's theorem holds in tropical geometry is maybe like, you know, a very good justification for the definition of intersection multiplicities that we did in previous slides. But like I said, it's not
question. So a couple of questions from the chat. First, is it stable under rotation of the plane? It looked like, okay. So the question says pi changes, which I may have, and then what's the definition of a primitive vector from an edge here? Shortest integral vector on E from P?
So let me answer both questions.
And then there's another question which, well, in Bézout's theorem in algebraic geometry, we also need to take into account possible intersections at the line at infinity. Is this the same for tropical curves as well?
Yes.
So
let me answer all questions. So the first
two questions there.
Is we're not allowed to rotate the plane, right? Remember that we're not just caring about a plane, but we're caring about a plane with an integral lattice inside it. Right? So a rotation is not a transformation that preserves the integral lattice, right? And in particular, curves will have, you know, a curve of degree D will have counted with weights, sort of D ends that run off to infinity vertically downwards, D ends that run off to infinity horizontal leftwards, and D ends that run off to infinity in a diagonal direction up and to the right, right? So if you really want to apply some transformation to this picture, right, then you might allow yourself to transform this with something that preserves the integral lattice, SL to Z, right? But let's not, you know, get into this because it will get us, you know, kind of sidetracked. So in general, best not to rotate the plane, right? The second question is, how about lines at infinity? So in classical algebraic geometry, you're gonna possibly lose some solutions if you don't consider the projective plane compactification. Here, I've sort of ignored this by again saying, let's already assume that the tropical curves intersect transversely, right? And in that case, there's not gonna be any issue of losing any points of intersection to something like it. Again, there is a difference between R2 and the tropical P2, but maybe that's you know, a discussion better left in another setting. And I forgot the third question. What was the third question?
It was the definition of primitive vectors.
Oh, primitive vectors. Okay, great. Thank you. So a primitive vector is a vector that, if you think of it as just a segment with an arrow, it has lattice length 1, right? So for example, in this direction, you know, slope 2, this is a primitive vector, right? In a horizontal direction, a primitive vector should actually be of length 1, right? So if I think of just a little segment, right, representing the vector and I forget the tail, primitive means it has lattice length 2, or, you know, there's no lattice point in between. Okay. Great. Thanks for the questions. And let's look at...
One more question is, does the intersection point have to be on the lattice?
That is a good question. It doesn't have to. No, it does not. Great. Cool. So let's verify Bézout's theorem. Let's see it in action for a second. Right. These are 3 pairs of conics, right? And the first pair of conics intersect. I have 4 points of intersection. These first 2 points, right? The matrix the primitive vectors are the standard basic vector, 1, 0, and 0, 1, right? So the matrix of the vectors expressed as column vectors is just the identity matrix, and the determinant is 1, right? And so each of these points counts with 1. And then I have two vectors right here, where one of the vectors is still the basis vector vertical one, so 0, 1, and the other vector is the vector 1, 1.
Renzo, a question: can you have negative multiplicity coming from orientation?
Yeah, so in our definitions, we're not doing that, right? We are just taking the absolute value of the determinant, right? So for example, the determinant for these 2 points, the way that I set up the matrix, I have the determinant is -1, but the absolute value, which is what we care about, is 1, right? And this, eliminates the ambiguity of having to choose which of the orientation the edges have, okay? So in this case, we have 2 black points that have multiplicity 1, we have 2 green points that have multiplicity 1, and the total is 4 with checks, right? So in the second example, right, we again have 1 point which has multiplicity 1, is exactly the same as what we saw before. Another point which is pretty similar to the green points has multiplicity 1. One of the vectors is 1, 0 instead of 0, 1, but 1, 0, 0, 1 is still a matrix of multiplicity 1. And maybe the more interesting point is this point right here.
Maybe, sorry, another question of, can you just explain a bit more how you get the matrices?
Yeah, so let me maybe do it right here slowly for this point. Let me call this point Q. Right, so what is the multiplicity? A Q of gamma 1 and gamma 2, right? So first I have to take the weight, the product of the weight of the edges, and in this case it's just 1 times 1, right? And then what I have to do is I have to take the absolute value of the determinant, and now I have to build a matrix, right? And you have to look at the primitive vectors in the direction of the 2 edges, right? So in this particular example, one of these primitive vectors is this one right here that I drew in blue, right? And this is the vector 1, -1. And so I'm going to have 1 minus 1 be the first column of this matrix. The second vector, let me change the color, is this one. Oops, it should follow the edge. Is this one. This is P2. So P2 has coordinate 1, 1. And so this 1, 1 becomes the second column of my matrix, right? And now putting all together, I get that this point has multiplicity 2. So
another question of, is there an easy way to know the weight of an edge just by looking at it?
The weight of an edge, just by looking at it, I mean, I think, it's usually you really have to look at one of the trivalent vertices from which the edge emanates. And, certainly if you're somebody like Hannah or Diane and have played this game for a long time, you just look at it and you know it. But I don't know that there is any like dirty trick other than doing it. Yeah. Okay, and so in the second case, we have 2 points of multiplicity 1 and 1 point of multiplicity 2. So again, we get 4, right, which is what we want. And in the last case, right, we have, 1 point of multiplicity 1. This is a point where the direction vectors are just the standard basis vectors. Another point of multiplicity 1 here. It should have been like a green point. And another point on multiplicity 2. So again, this is for. Okay. All right. So at this point, I would like for everybody to take a little bit of break from listening to me, but actually work together in groups in a mini problem session. And the goal of this mini problem session is to try to come up with a strategy of proof of this theorem. And this first exercise is going to lead you to hopefully discover you may want to prove tropical Bézout's theorem. So what I would okay, so as we wait for everybody to kind of come back in the rooms, let's just answer a couple questions about the mini problem set. So maybe I should have said this. So the weight of an edge, right, is a datum that has to be given, right? So if, since I did not give you the Newton's substitution that gives rise to L1 and L2, then technically I didn't give you all the information, right? I just wanted to assume that L1 and L2 are given the same weight. So whichever weight it is, it doesn't matter, but so long as it's the same weight, then this statement is going to be true, right? And again, to just summarize in maybe just 30 seconds what this exercise was about, right? What we should have noticed is that if, the edge of a tropical curve, right? L1, we called it a line, but really we could think of it as an edge because every statement we were making is really local to just a neighborhood of a point of intersection. But if you slide an edge of a tropical curve past the vertex of another tropical curve, then the multiplicity of intersection does not change, right? And this really came down to the balancing condition and the fact that the determinant is a multilinear application, right? So I visited a few breakout rooms and most everybody seemed to have realized that, but just to say it out loud. And then once you know that, the multiplicity does not change as the edge of one curve passes by the vertex of another, and you have to, worry a little, maybe not all vertices are trivalent, but the same statement is going to hold. Then you can actually move one of the curves, in such a way that the two curves are in a relative position where it's very clear that you have D1 times D2 points of intersection. So that's the strategy that I had. Now, if this is still a little bit blurry, tomorrow you can, work on refining these details during the problem sessions with Andy. Andy will be happy to help. All right.
And there's one more question before you get started, which is, if we have a tropical curve not coming from a subdivision of size D, how do we find the degree?
So right now, again, for the point of view of this first half hour of the talk, degree D means that it has to come from a subdivision of a triangle of size D. So this is just not part of the framework that we're looking at right now. We'll look at, you can have different notions of degrees. You can have different notions of plane curve, maybe like instead of embedded as maps from curves. As the context changes, we'll clarify this. Yeah. Okay, so if there's no more questions about the mini problem session, we can move out to the second part of this lecture. We're gonna change a little bit of topics, right? Right now we have done our first correspondence theorem in, embedded curves tropical geometry, right? Bézout's theorem holds tropically. Now we're gonna switch a little bit of our perspective, and just like in ordinary differential geometry, at some point, you switch your point of view from looking at embedded manifolds to looking at abstract manifolds. We're going to introduce the notion of an abstract rational tropical curve. And so an abstract rational end-pointed tropical curve is a tree, T, and it has n labeled ends, and a function, which we're going to call the metric, that basically assigns a non-negative length to each edge. And we're going to call a abstract rational tropical curve stable if each vertex has valence at least 3. Okay. So in particular, here we have an example of a stable rational curve, right? I have 3 vertices, I have 7 ends, and in gray, I'm denoting this pi and this 5. These are the lengths of the edges. And here I have 2 non-examples, 2 examples of things that are not abstract rational stable tropical curves. This first example is not stable because this vertex V2 is only 2 valent. And this example right here is not rational, and sorry, this square root of 2, oh yeah, is the length of this loop, is not rational because now I have a loop. Right? So the Betti number of this graph is 1 and it's not 0. Or if you want, this graph is not a tree, it's not contracted. Fundamental group of rank 1. Okay? Great. So let me mention a couple conventions that...
Sorry, there was a question about, do you assign length only to internal edges?
So yeah, so this is a great question. So let me answer it as I talk about the conventions, right? So the ends, the edges that are not internal, we're going to consider them to be unbounded. So if you want, you can think of them as infinite length, or you can think of you're not assigning length to those edges. And we're also not thinking that there are endpoints, right? So an end has only one vertex, which is the one that attaches the end to the finite part of the graph. So another convention, another notation that we're going to use is if we forget the information of the metric, so we say, okay, now forget the lengths of the edges, then we just get a stable tree, and we're going to call this the topological type of the tropical curve gamma, of the abstract tropical curve gamma. And the other thing I wanted to point out is we have allowed ourselves to give value 0 to the length of a tropical curve. I say that the length should be non-negative, right? And so let me draw in an example what I mean. So we're going to impose an equivalence relation on our tropical curves, which is if the length of an edge is 0, then we're going to declare this tropical curve to be equivalent to the tropical curve where you contract an edge. Okay? So we're going to define this the equivalence relation as generated by every time an edge length is 0, you can contract it. And with this convention in place, right, then the set of all tropical curve of a given topological type is parameterized by a cone, which is the non-negative real numbers to the number of compact edges, right? So for example, again, let me draw a picture here. If I have a topological type that looks like this, 1, 2, 3, 4, 5, this is equal to T, right? Now I have 2 edge lengths, X and Y, and I can think of my tropical curves of type T to be parameterized by this orthant in the plane, where I'm including the axis and I'm including the vertex, right? But I'm secretly thinking that this vertex represents a point where I have contracted all edges. Okay. Great. And so what are we going to do? We're going to create a moduli space or parameter space for all possible stable, abstract, rational, and pointed tropical curves, right? And it's going to be a cone complex, right? Any topological type is going to give us a cone, right? Which, think of it as some positive orthant in some r to the n. And then we're going to take the disjoint union of these cones, and then we're going to glue them according to the equivalence relation that we just defined, right? We're going to glue points that correspond to two tropical curves, gamma and gamma prime, that might have different topological type, but that become the same tropical curve after contracting all edges with length 0. Okay? So let's, again, definitions are often more confusing than looking at examples. So let's look at M04 trop, this example, right? So in gray, I'm showing the 4 topological types of 4 pointed stable tropical curve, right? I have one topological type here that parameterizes curves that have no compact edges, and 3 topological types where the curves have exactly one edge, and it separates the marks, 1, 2 from 3, 4, 1, 3 from 2, 4, and 1, 4 from 2, 3. I have denoted here by x, y, and z the length of that edge, right? The set of all possible lengths is array, is r greater than or equal to 0. So I have 3 rays and 1 vertex, and when I give length 0 to a tropical curve with a compact edge, I declare it to be equivalent to the tropical curve I obtained by contracting that edge. That means that the vertices of this 3 ray are all glued together with the point that corresponds to the tropical curve with no compact edge. And so my moduli space M04 trop consists of 3 rays attached to the point, right? Okay, of course, at this point, 3 rays attached to the point is all that I can say, but as you can see from the picture, I drew these 3 rays in not a random configuration. I drew them as a tropical line, if you want, or as the rays of the fan of P2, if you want. And this is not random. This is a choice, right, that I've made. And in the next few minutes, we'll understand that, in fact, M04 trop can be thought as a tropical line, right? Which is, again, this is in itself another example of a correspondence theorem, because in classical algebraic geometry, M bar 04 is P1, right?
So Renzo, we have a few questions in the chat.
Yeah.
The first is M0n trop the same as the space of phylogenetic trees?
Yes.
And how will it look at a, and then the second question from someone else is, how will it look at a curve at the point xy0 in the parameter space?
So I'm not sure I understand what the question is, xy0. So I guess we should, maybe let me say the way I think of this, x, y, and z's, I'm not thinking of them as coordinates on a 3-dimensional space, right? I'm thinking of x as being a coordinate on this diagonal ray, y on being a coordinate on this horizontal ray, and z as being a coordinate on this vertical ray. And so if we're living in a plane, they're not linearly independent functions, right? I hope I...
And then there's a question asking whether the marked vertices are permuted. Is this the case?
Mapped vertices are permuted. I'm also not sure I fully understand, but let me try to interpret. So what this tropical rational abstract curves have no automorphisms, right? Because what is an automorphism of one of these curves? It would be a map from a graph to itself, but this map has to preserve all the data, which includes the labelings, right? So this 1, 2, 3, 4, this labeling of the ends are part of the data that I want to permute, right? So if you're thinking, oh, well, this is a graph that I can flip vertically, and if I flip it, I don't notice it, so I should be able to permute these two vertices and permute these pairs of ends. We're actually not allowed to do that because doing so would sort of also permute the labeled ends, and that's not something that we can do. I hope I have interpreted the question correctly. Okay. If there's no further question, let me move on, and we say, okay, we have this cone complex, this abstract cone complex that parameterizes all possible rational end-pointed stable tropical curves, but we want to see it as some kind of tropical object in and of itself. And so let us try to embed this cone complex into a vector space. Okay? So it's going to take us a little bit to get there. So let's first introduce this couple functions. The first is the linear function phi from r to the number of n's to r to the n choose 2, that to a vector a1 to an assigns, n choose 2 coordinates and the ijth coordinates. I can think of n choose 2 as selecting 2 out of these n components of r to the n, and the ijth coordinate of this vector with n choose 2 coordinate is ai plus aj. I'm going to do an example in a second. And what we're going to do is we're going to actually look at the image of this linear map, and we're going to quotient r to the n choose 2 by the image of this map. Okay? We're going to get a quotient space, which is dimension n choose 2 minus n. And we'll see why this is useful in a second. Just hold on, right? The next thing we're going to do is we're going to consider the distance function from m0 n trop to r to the n choose 2, right? And let me draw some pictures as I say this. And again, suppose that I have a point 1, 2, 3, 4, 5, and that I have lengths, maybe length pi and 2 pi for these edges. So this is a point in M0, 5 trop. And I'm going to map this to a vector. Not going to write all r to the 5 choose 2, right, which is r10. I'm not going to write all the 10 coordinates, right? But for example, I have a coordinate that I want it to correspond to the choice 1, 2 out of the 5 indices, right? And what am I going to do? Well, I'm going to look at the distance between the point 1 and the point 2, right? And this distance in this case is 0, right? If I want to look at the coordinate 1, 3, then I'm going to walk from 1 to 3, and I'm going to traverse an edge of length pi, and so this coordinate is going to be pi. Let me do one last example. Here I look at 1, 5. Maybe that's not the natural ordering, but I would be walking from 1 to 5, and so here I traverse a length of 3 pi, right? And so I can go all possible pairs of ends, right, and look at what is the distance between them, and that's this the value of this map at this point in M0 trop pi. So this map embeds M0 and trop in R to the n choose 2. But this embedding is not desirable, is not a tropical object, is not balanced. It doesn't satisfy a balancing condition that we haven't introduced yet. We'll actually introduce this on Wednesday. But again, think of some generalization of the balancing condition for a tropical curve, right? And because this image of M0 and trop in R to the n choose 2 is not balanced, we do something to R to the n choose 2, which is we quotient out the image of phi, right? Map further down to Q, right? Now we have a map from M0 and trop to Q, which is still an embedding, right? And in a second, we'll make the statement that this embedding is balanced. But before we do that, let me maybe give another way of thinking about combining these two maps together, right? One way so that you can think about combining these two maps together is that you can actually assign lengths, you know, L1, L2 to the compact edges, and you can assign lengths A1, A2, A3, 4, and A5, right, to the ends, right? And now you can think of a map, you know, dist, oops, white will not write very well. The map dist from 0 n trop to R to the n choose 2, which is defined as before, like the ijth entry of the output vector here is the length of the segment that I have walking from the end I to the end j, but now the non-compact ends also have lengths A1, A2, A3, A4, A5. But then we want to not care, right? Then we want to not, then we want to deliberately not care about the length of the AIs. Okay, and not caring means that we just take a quotient, right? We quotient by the effect that is being had on this map by having lengths on these edges. Okay, and so we have a map from M0 n trop into a vector space of dimension n choose 2 choose n. And the theorem is that the image of dist M0 n trop with all cones taken with weight 1 is a balanced marked fan in Q. Again, we're going to define what balanced and marked fan means on Wednesday. I didn't want to do it today because otherwise I would have had a full Monday lecture of kind of what I think are highly boring lattice geometry definitions. I wanted to introduce the geometric notions first. So, you know, Wednesday, we'll define this in detail. But like I said, let's think of this as a generalization of the balancing condition for a tropical curve. And since M04 is dimension 1, then we can verify that in this case, this actually is the same as saying that M04, when it's embedded in this quotient space, it is balanced as a tropical curve, right? So
Renzo, there's a question. Does this mean you can choose non-zero AI to get a balanced marked fan and R to the n choose 2?
Yeah, this is a classical question. It should be obvious. I think that's not, well, no, maybe that, yeah, that should be possible, right? Because,
Well, I guess if you take all of them, maybe, but
yeah.
including negative ones, though, I guess.
Yeah, including, sorry, you're totally right. So remember that by, right, the AI is technically, we allow them to be positive and negative numbers, right? So if we allow AIs to be also negative numbers, right, so which is kind of weird if you want to think of them as length, but then you're certainly going to be able to sort of move your fan in such a way as to be balanced. If they're only positive, then no, and we can see it in the example right here for the M04, right? So I've written the 3 primitive vectors for the rays of M04, or, these are tropical curves with one edge, compact edge of length 1, right? And the coordinates, the 6 coordinates are to the 4, choose 2 for the first topological type, where I have 1, 2 on one side and 3, 4 on the side. On the other are 0, 1, 1, 1, 0, 1. Right? And then you can read the second and third line. And if you add up these 3 vectors, we get the vectors with it constantly equal to 2, which is phi of 1, 1, 1, 1. Right? So this is a non-zero vector in R to the 4, choose 2, but it is in the image of phi, so it becomes 0 to Q. So this is balanced fan. Okay. So something similar will hold in higher dimension, but we'll talk about the details next time. So one more thing I want to talk about in M04 are what are called tropical cross ratios. And given 4 n's, that I'm going to call I1, T1, I2, and T2, we're going to define the tropical cross ratio psi from I1 to T1 from I2 to T2 is going to be the sine length of the intersection of the path that connects I1 to T1 with the path that connects I2 to T2.
Sorry, Renzo, one more question.
Yeah.
Is the map from M0n trop to Q an embedding? And then the next question is this obvious?
This is an embedding. It's not obvious, but it's a simple exercise that you can do in the problem session. Yeah, right. Yeah, but it is an embedding. Okay. Great. So let me illustrate cross ratios in the picture. Right here, I have a topological type or an abstract tropical curve with 10 ends, right? And I've selected I2 and T2 to be these 2 ends, I1 and T1 to be these 2 ends, and then in red, I've drawn, a directed path from I1 to T1. In blue, I've drawn a directed path from I2 to T2. This dash part in the middle is the intersection of the 2 directed paths, right? And the length of this dash part is minus the cross ratio, I1, T1, I2, T2. Okay? And notice that these are functions from M0 and trop to R. And the reason I wanted to highlight this notion of tropical cross ratios, well, is twofold. First, I'll say the one which is dear to my heart, which is the way that one works with moduli spaces is you try to construct functions on the moduli spaces by using the geometry of the object parameterized. And this is exactly an example of doing that, right? So
there was a question about the minus sign. Does that come from the orientation of the paths?
Yeah, so the reason I put a minus sign, right, is because the path from I1 to T1 and the path from I2 to T2 traverse this common area in opposite directions. And so this quantity is going to be negative. This length, this dash length is going to be minus the cross ratio, or if you want, the cross ratio is going to be minus that dash length. But again, let me hit this home one more time, right? That it's a function on a moduli space that is constructed by using the geometry of the objects parameterized. This is a standard, extremely useful yoga of working moduli space. The other reason why these are really important and interesting is that this whole picture of M0n being embedded in R to the n choose 2 minus n as a balanced fan is actually a parallel picture to the embedding of Grassmannian G to n via the Plucker embedding, and then taking the quotient by an action of a torus to obtain n bar 0n. I'll say more of that in a second when I get to the next slide. But let me just conclude by saying that one can actually use tropical cross ratios to prove that M0n trop is balanced. So this will be an exercise in the problem sessions that I highly recommend for people that maybe are a little bit more already experts in tropical geometry. And that's it. So in the next slide and for the next 5 minutes, I just want to sort of wrap up this lecture by mention a little bit, on the fly of what happens after this, right? And maybe also what happens during this, right? So as I mentioned, first of all, this whole story of M0n trop being embedded in a vector space comes from the fact that M0n trop is, in fact, a tropicalization of M0n, classical. If you think of M0n as living inside a torus, and this is the torus that you obtain by embedding the Grassmannian Gn2 via the Plucker embedding, and then taking a quotient of an action of an n-1 dimensional torus acting on the rows of your matrix. So this also shows that M0n trop gives what's called a tropical compactification. This is work of Cavalieri. What does this mean? So M0n trop is a balanced fan in a vector space. And for people that know and love toric geometry, if you have a fan in a vector space, you get a toric variety. M0n is embedded in a torus. And if you take the closure of this M0n inside the torus in this toric variety, you get m bar 0n. So the classical moduli space that compactifies M0n arises as the compactification of M0n in a toric variety that's given to us by the tropical moduli space. That's the notion of tropical compactification, and it's very useful and very important. In particular, Diane and Angela Gibney studied this embedding and gave us equations for m bar 0n in the Cox ring of this toric variety x delta. X delta is the toric variety obtained by the fan. It's a toric variety associated to the fan of m bar 0 of M0n trop. From this, several people have studied variation of M0n trop. In particular with Simon Hampen, Hannah, and Dhruv, and independently Martin Ulrich studied tropical Hassett spaces. These are spaces where the stability condition is modified, where you're given weights to n, and you're saying, well, the valence 3 condition has to be substituted with a total weight of the edges around each, where compact edges have weight 1, but non-compact edges have lower weight, and you need to reach a critical mass to be able to be stable. And you get moduli spaces that are typically kind of contractions of the other tropical moduli space, and if you ask yourself, when are they tropical compactifications? This work I've studied that. Very recently, Andy Fry, who will be leading the problem sessions tomorrow, has further generalized, or rather kind of generalized to a different case where the stability for tropical rational curves is given by a graphic matroid. And I'm sure Andy will be happy to talk to anybody who's interested. The next step, which I credited to a few people here, but it's surely not being complete, but certainly Grisha Mikalkin and Kerber Markwig, Lars Allerman and Johannes Raus and Eric Katz, all should be given credit for developing intersection theory on M0 and trop, so being able to actually solve enumerative geometric questions of intersection theory. And then in the last 3 bullet points, we're actually abandoning the genus 0 case. The problem with higher genus graphs, right, where you're not rational, is that you do not have, MGN is not embeddable in a torus in any reasonable way. And so there's not a natural way to have MGN trop. I mean, actually, there's no way for MGN trop to live in a vector space. And so what is the relation between MGN trop and classical MGN? It has to be a little bit more refined, right? And so there's 3 layers that I want to mention real quick. The first is, Abramovich, Caporazzo, and Payne realized that there's a strong connection between MGN trop and the analytification of MGN, which means an MGN over all possible valued field kind of at the same time, right? And the statement is that MGN trop is a skeleton of MGN analytic. I believe that this will be something that Erika Mazzon will talk about in a couple of weeks, and promise it'll be very exciting. And then in work with Melody Chen, Martin Ulrich, and Jonathan Wise, we promoted the notion of MGN trop from being a moduli space to being a moduli stack. So in particular, allowing ourselves to use the moduli space dictionary a little bit more. And finally, in ongoing work with Hannah Markwig and Andreas Gross, we have further promoted this notion of cone stack to being a stack over a category of tropical spaces where we can actually perform intersection theory. So this, sorry, this was a handful, it was very fast, but I know there's some people in the audience that are orienting themselves in the field, and so hopefully this provides a roadmap for possible further reading. So in the last slide of this talk, there's a bunch of an incomplete bibliography. There's titles. I didn't add the rest of the bibliographic information because it would make the slide not fit. But if you Google any of these titles, you'll be able to find corresponding article very easily. And that concludes my first lecture. Thank you all so much for hanging in there, and